Hi, I'm Carlton Coffrin. In this video, I'll give a brief introduction of PowerModels' network model with a specific focus on some updates that we've made in version 0.6. Before I get into the details of the network model, let's talk a little bit about the design motivations for the particular model. Our primary goal here is to do R&D on industrial transmission system datasets. It's important to note that there's generally a lack of realistic network datasets, and this has been presenting a significant challenge for doing R&D on transmission systems. ARPA-E, for example, has started the Grid Data program, where different teams are working to develop more realistic transmission system datasets. Now, it would be great to use these for doing R&D. However, the Matpower network model, which is now the de facto standard for R&D, lacks some features that are needed to represent these more realistic industrial-grade network datasets, and we'll get into that in a bit more detail later. So, what are our goals in designing this new network model? Our first observation is that the simplicity of the Matpower network format has been very successful. It's allowed researchers to focus on R&D on the modeling challenges and not necessarily the software engineering details. Supporting these industrial-grade network formats in their in all their detail requires a lot of engineering. And to that end, PowerModels adopted the exact same network model as Matpower in versions before 0.6. And so in this video, we'll be discussing why we went beyond that basic model. So our primary design goal will be to design a minimalist extension to the Matpower format, which can accurately support these industrial transmission datasets. Our goal will also be to make these industrial transmission system datasets easily accessible to power system researchers through having a parser and a translator into this simpler format. We have nominated PSSE version 33 as our standard industrial data format. Why have we used this one? The first reason is that it supports bus voltage bounds, which are a core part of AC/OPF studies, so we would very much like to have those in the data format. And then our second reason is that we observe that it's sufficiently accurate to represent the bulk of FERC 715 filings, which we presume is a fairly accurate model of what a transmission system dataset for system planning is. So what are the differences between Matpower versus PSSE? Doing a detailed analysis would take quite a long time, so I'll just give an intuition using set diagrams. So in these pictures, I'm going to draw circles, and these circles will represent all the possible mathematical models that could be defined with one of these formats. So let's say that this particular circle is indicating all the models you could write and encode in the Matpower format, and this is the circle for all the models you can include in the PSSE format. So the first thing to notice is that there are some things that Matpower has which PSSE does not. For example, fuel costs for generators is included in Matpower, fuel cost functions I should say, but it's not in PSSE. Meanwhile, there are many features of PSSE which are not in Matpower. For example, there are fax devices or various different types of HVDC lines, and so those are all the things which exist in PSSE but not in Matpower. So as I mentioned before, supporting all of PSSE is too much. This circle is too big. So what we want to do is first determine a high-value subset of this format to support. So we're going to define a PSSE subset like this. And then we're going to look at, okay, what is the union of the Matpower format and our restricted PSSE format? And this is what the network model for PowerModels will be, something that can include both of these things in their entirety. So let's talk a little bit about developing a high-value subset of PSSE. At the high level, these are all the different types of components that are in a PSSE data file. After doing some investigation and looking at different network files, we reduced this set down to this particular amount. So it's important to note here that for the loads, we're removing the Z and the I component and just looking at constant power. And then for these other particular component types, we're just going to remove them entirely. And what we've observed is that if you support this reduced set of components, you can cover at least 99.97% of all the components in industrial transmission system datasets. Now, it's important to note that in the parser we will develop, we will parse all of the data that's in the PSSE file, but we may not incorporate some of the fields of those components into our optimization models, and I'll just highlight some of those now because they're quite interesting. For the PSSE buses, they include both a nominal voltage rating and an emergency voltage rating. We will not include the emergency voltage rating in our optimization formats, at least for now. In terms of the loads, they have an I and a Z part, but we're going to ignore those. There are switch shunts, which have parameters on how you can configure those, and we'll just fix them to their nominal value, so we'll kind of ignore the switching parameters in there. And then for 3-winding transformers, we're going to break those into multiple components so that we don't need an explicit component for a 3-winding transformer. In terms of the PSSE DC lines, there are 2 terminals and VSC versions, and we're going to ignore many of the engineering constraints here because we're going to map them to a much simpler HVDC line model. So let's talk a little bit about the data model and the mathematical model that is implemented now in PowerModels. If you look at the version before version 6, the main changes that we're going to make are we're going to add new component types for loads and shunts, and then we're also going to generalize the branch model. So I'll talk a little bit about what each of these generalizations is. We're going to focus on supporting the component parameters that are the exact same as Matpower. So basically, we're going to use the exact same naming system from Matpower, but we will just generalize some of them slightly. So yes, the component parameter names will follow the Matpower conventions, and then our primary changes will be that there's lists of loads and shunts instead of one per bus, and then we'll have to generalize the branch model a little bit, and I'll get into the math of that later. So let's talk a bit about the component mapping. On the left, we have all the components in Matpower. In the middle, we have the PowerModels component list, and on the right, we have the subset of PSSE that we're interested in supporting. So this is how the things map in Matpower. In Matpower, the bus records include both the load and the shunt value. These will be broken into 3 separate components, so we have explicit loads and shunts. And then all of the other components will pretty much map one-to-one over to the PowerModels format. In PSSE, we'll take the fixed shunts and the switch shunts, and we will merge them into the generic shunt element in PowerModels. The 3-winding transformers will be broken into multiple components, 1 star bus, and then a number of 2-winding transformers. And then all of the DC lines, the 2-terminal and VSC, will be mapped into this simple HVDC line that's included in Matpower. And then the rest will map over pretty much one-to-one. Now it's important to note, and I mentioned this previously, that some of the fields in these component mappings in PSSE will not be supported by PowerModels, but they will be included in the data format just for completeness. So given that we're going to do this mapping, how are we going to generalize the Matpower mathematical model to support all this? So this is the basic power flow balance equation in Matpower. And notice that this is one equation for every bus. We have 1 demand and 1 shunt. What we're going to do in PowerModels is just generalize the single demand and single shunt to a list which can be where there can be multiple of them at one bus. So the main change is that these, instead of being single values, are now going to be sums over collections of values. It's not a huge change to make. Here is what the Matpower branch model looks like for an AC line and a 2-winding transformer. It supports both of those components. And probably the most interesting thing here is that the line charging parameter is just one value, BC, which is evenly split on both sides of the line. The PowerModels branch model will be slightly more general in that the line charging parameter will be a full complex number, which includes both a conductance and a susceptance, and it can be different on either side of the line, so it will be asymmetric. So the main change that we're making here is that we're going to generalize this particular parameter, and you can imagine that it's quite easy to map Matpower into this more general model. So given that, how can we encode the PSSE data into this more general model? Here's the equation that we have in PowerModels for a particular branch, and let's look how we encode an AC line in PSSE into this model. So the AC lines in PSSE look like this, so they don't have the transformer parameter, but they do have this asymmetric line charging parameters. So all we need to do here is replace the transformer parameter inside of the PowerModels branch model with 1, which is like the identity, and then we'll get back an exact, mathematically exact version of the PSSE model. The next thing that's a little bit more interesting has to do with how we implement two-winding transformers in PowerModels. So again, we have our general branch model from PowerModels, which looks like this, and this is what the PSSE two-winding transformer model looks like. So all we're going to do here is we're going to move the magnetizing admittance in the two-winding transformer for PSSE, and then put it as a line charging parameter in PowerModels, and then ignore the second line charging parameter inside of PowerModels by setting it equal to 0. So this will introduce a slight approximation because we will be pushing the magnetizing admittance through the transformer parameter, but based on our experiments, it has not made a significant difference in the power flow solutions, so it seems like a good trade-off of simplicity and accuracy. The last component that's of interest is this three-winding transformer. So inside PSSE, the data is provided in this particular form. What we're going to do is introduce, for every one of these three-winding transformers, an explicit star bus, V star, and then we're going to implement it as three two-winding transformers where we've calculated an admittance to the star bus for each one of these particular voltage points. Again, we'll do the same approximation where we take the magnetizing admittance for the three-winding transformer and then put it on the first transformer winding here. And again, we've observed that this is not a particularly significant change in terms of the mathematical solutions we've seen. So we think it's a fairly reasonable approximation to make, and it keeps the model fairly simple. So given those transformations, let me just go over a kind of a basic ACOPF type of formulation that you'd have in PowerModels, so you can see that after we've mapped these particular formats into the PowerModels data structure, we can easily support this wide variety of test cases. So this is the data that is coming through in an abstract sense inside of PowerModels. You have a set of buses, you have a collection of reference buses just in case there are multiple independent components in the network. You've got your branches, both forward and reverse directions, generators and the subset of generators that occur at each bus, loads and the subset of loads that occur at each bus, and shunts and the subset of shunts that occur at each bus. Then for each one of these different types of things, we have particular data. So we have generation limits, both real and reactive power, or active and reactive power. We have the generation fuel cost parameters, which are coming from Matpower. We have voltage bounds, which are in both formats. We have power demands, a collection of those, bus shunts, and a collection of those. Branch parameters, these are like the static parameters for charging, admittance, and transformers. And then you have the branch limits, like the thermal limit and the angle difference limits. Given all that data, we can state a kind of general ACOPF problem like so. We have decision variables for the amount of power the generators will inject. We have the voltage variables and also variables for the flow of power on the lines. This is a quadratic fuel cost function, which uses the particular constants that are provided in the data. We have our reference bus constraints, which fix these particular buses in the network to an angle of 0. We have our generation bound constraints, which make sure the generators output within a reasonable active and reactive power box. Here's our voltage magnitude bound constraints, our power balance constraints. We have our branch flow in the forward direction and our branch flow in the reverse direction. Notice because of the asymmetrical line charging and the transformer parameter, these two values are asymmetric. Then we have our thermal limit and our voltage angle difference. So not a particularly complicated model, or not particularly more complicated than Matpower, we can say, but you've seen before how we can map, say, a PSSE dataset into this fairly simple power model. It's worth noting here that we didn't treat DC power lines here, HVDC, but we do implement the version of that which is from Matpower, and it's a fairly simple model where there are two power sources at the two buses, and they're linked together through a simple constraint which can account for some linear losses on the DC line. So just to summarize what we've discussed here, I've given you an overview of PowerModels Mathematical Model for version 0.6. We've shown how this format can support reading both Matpower and PSSE files and in one shared data model. It's a minimal extension of the Matpower format, with the main change being that branches have this asymmetrical line charging value, but still we can support industrial grade datasets, for example, the ones that come from FERC 715 filings. The key components from PSSE that were interesting to handle here were 2 winding transformers, because we had to go from a T model to a pi model, 3 winding transformers, and then these fixed and switched shunts. How are you going to reconcile those 2 types? All of these extensions are currently available in the open source version of PowerModels.jl. Any version after version 0.6 will have all of these features included. So I hope you enjoyed these extensions, and I hope they help you in exploring some industrial grade power system datasets.